So we are looking at the limit as t is approaching -4, t cubed minus 6t plus 40, all divided by t squared minus t minus 20. If we go in and we do direct substitution in here, we have -4 quantity cubed, that is -64. A -6 times a -4, so that's plus 24, plus 40, all over -4 squared is 16. And then we have minus a -4, so that's plus 4 minus 20. So we get that indeterminate form of 0 over 0. So we can apply L'Hopital's rule. So we're looking at the limit as t is approaching -4, and we're going to look at the derivative of the numerator divided by the derivative of the denominator. So the derivative of our numerator gives us 3t squared minus 6. All over, derivative of the denominator is 2t minus 1. So now we're going to do direct substitution again. And so if I square -4, I get 16. So I have 3 times 16 minus 6 all over 2 times -4, which is -8. Minus 1. 3 times 16 is 48 minus 6 all over -9. So I have 42 over -9. Those are both divisible by 3. So it's -3 goes into 42 14 times all over 3. So it looks like my answer is -14/3. So if we look at this limit as x is approaching infinity of 3x cubed minus 5x, all over 7x cubed plus 6. And so we're getting this infinity over infinity, which is in a lot, tells us it's an indeterminate form. And we can look at L'Hopital's rule, which tells me to take the derivative of my numerator, which would give me 9x squared minus 5, all over the derivative of my denominator, which is 21x squared. So again, I can see that when I plug in infinity for x, I get infinity over infinity. And so I'm going to want to use L'Hopital's rule again. And so we're going to take the derivative of our numerator, which is 18x, all over the derivative of our denominator. Derivative of our denominator is 42x. So notice we can simplify here. We both have an x in common. And we have 18 over 42. A limit of a constant is just that constant. And so let's just reduce this. I notice 6 goes into 18 3 times, and it goes into 42 7 times. And so our answer is 3/7. I just kind of wanted to show you this though. If we thought about this from previously, when we got infinity over infinity, we could divide by that variable raised to that highest power. So if we did that in the denominator, so multiplying by a fancy one, that fancy one we're going to multiply by is 1 over x cubed. 1 over x cubed. And so if you distributed that, notice how we get the limit as x is going to infinity, but 1 over x cubed times 3 over x cubed, that just leaves us with 3, minus 5x divided by x cubed, that's 5 all over x squared, divided by, distributing this, we have 7x cubed over x cubed is 7, plus 6 over x cubed. And so now if we do our direct substitution, a number in the denominator going to infinity makes this thing go to 0. So 6 over x cubed as x goes to infinity also goes to 0. And so we're just left with that 3/7. So again, there's different ways that you can approach it, but it will get the same result if we can use that one, if we can use L'Hopital's. So the next problem says use L'Hopital's rule to find the limit as theta goes to 0 of 5 raised to sine theta power minus 1 all over 3 theta. I notice if we do direct substitution, we would get this was equal to 5 sine raised to the 0 power minus 1 all over 3 times 0. Sine raised to 0 or sine of 0 is 0. So this gives us 5 raised to the 0 minus 1 all over 0. Well, 5 to the 0 is 1. And so 1 minus 1 is 0 all over 0. So it's that indeterminate form that we can use L'Hopital's rule. So I notice that when we're looking at the derivative of 5 raised to sine theta, we're going to need to use the chain rule. Our base is 5. And so when I take the derivative, that's going to give me natural log of 5 times itself, 5 sine theta, times the derivative of my exponent. So derivative of inside sine theta, that's cosine theta. Minus the derivative of 1 is 0. All over derivative of 3 theta, that's just going to give us 3. So let's see if we go in here and we plug in 0 wherever we see a theta. And so if we do that, we get the natural log of 5 times sine of 0, or 5 raised to the sine of 0. So that's really 5 raised to the 0 power. And cosine of 0, that is just 1, all over 5. So I see that we're left with just natural log of 5 divided by 5. Well, it's helpful if you carry the correct number. This should be a 3 here. This should be a 3 here. So the following problem is a review problem. It says use logarithmic differentiation to find the derivative of y with respect to x. And so what we want to do is we want to take the natural log of both sides of our equation, because taking the derivative natural log is easier than any other base. So we're looking at the natural log of y equals the natural log of, I'm going to rewrite this, of my quotient x all times x minus 8 divided by x squared plus 9. And this 7th root is the same thing as raised to the 1/7 power. So we can use rules of logs to bring that exponent down. And so we have 1/7 of the natural log of this quotient x all times x minus 8 divided by x squared plus 9. So rules of log says if we have a division and we're taking division, natural log or log of a quotient, we can break that down with a minus in between. And so doing that, we would have natural log of y equals 1/7 natural log of my numerator, x times x minus 8, minus the natural log of my denominator. And the natural log of my denominator is this x squared plus 9. I need brackets around this whole thing because of that 1/7 power. And then I notice I can break this down a little further because of this multiplication of this natural log. And so if we have multiplication and we're taking the natural log of a product, we can break that down with addition in between. So bringing everything down, I have the natural log of y equals 1/7 times the natural log of the first x plus the natural log of the second, which is x minus 8 of the product, minus this natural log of x squared plus 9. So it's now in the form that it's going to be pretty easy to take the derivative. And so we're going to take the derivative of both sides of our equation. Remember, y is a function in terms of x. So when we take the derivative of natural log of y, we need to use the chain rule. So the derivative of natural log of y is 1 over y times the derivative of y, which we can call dy over dx, equals 1/7 times. So we're taking the derivative of the natural log of x, which is just 1 over x, plus the derivative of natural log of x minus 8, which is 1 over what we're taking the natural log of, x minus 8, times the derivative of the inside, but that's just 1, minus the derivative of this natural log of x squared plus 9 is 1 over what we're taking the natural log of, x squared plus 9, times the derivative of the inside. And the derivative of the inside in this case is 2x. And then we want to multiply both sides. We want dy dx by itself. So we want to multiply both sides by y. So doing that, we get dy dx is equal to 1/7 of 1 over x plus 1 over x minus 8 minus 2x all over x squared plus 9 times y, but y was this same thing as the root, 7th root of x all times x minus 8 all over x squared plus 9.